All right, so I want to talk more about the general form of the transportation problem, mainly because linear programming models tend to be presented in a more general form first, and which can sometimes make it a bit harder. So what I wanted to do with the previous example was actually start with an example and then move it up into the general abstraction. So now, this is not the this is not the the one way to say the generalized transportation problem. There's a lot of modifications we can give, but fundamentally there is a core model or core set of ideas that we can effectively say, okay, these problems is similar to the transportation problems, and therefore we can adjust to it, and therefore there is a known solution. So as said before, consider a set of M factories. Oh, I wanted to use the highlighter there. M factories serving a set of N customers. So what happened there before was that in the previous example, the factories were actually the water storage, and then the customers were the water dams that basically needed water from the storage. So we wanted to find it. So I'll probably just jot that down quickly. So in this case, the factories were the source, suppliers, and then the customers in this case were the dams. But then customers going to be storefront, that kind of thing. So we defined decision variable xij to represent the amount shipped from factory I to customer J. So effectively that is in that, well, that's the only decision variable we're going to use, but as said before, it's got two dimensions, so it's not just one decision variable, but x times j number of decision variables. And in this case, we got the cost of shipment, which as said in the notes is represented by travel distance before from factory I to customer j is Cij. And so this is actually a parameter. So the Cij is what we call a parameter. And as said before, what parameters tend to be in linear programming models, and I guess models in general, is that they are placeholders for numbers that are going to be eventually supplied. However, right now when we're talking about a general form, we don't know what those numbers are. So therefore, we just say, okay, but we know there's going to be a cost. We know there's going to be a cost for each of them, and as such, we are just going to have a placeholder, a parameter, to represent those particular numbers. So moving on, so we got the typical constraints, which is the demand and supply constraints. So remember that in the table, we were going across the row for the supply and then going down the columns for the demand. And what you have down here is the general form. So notice, if you're unfamiliar with this notation, it can help to be a bit more, like, I guess, to notice to kind of pay attention to each of the indexes to see what's going on. So remember how we had a table before, and we were kind of just saying, okay, so I'm just trying to think. So supply 1, supply 2, and then customer 1, 2, and 3, and then so that's xii, and then some amount. Sorry, xii and some amount, x12, x13, x21, x22, x23, and then what we had before was that we had the supply amount on the right here. So the supply in this case is now going to be si. So and then not s. Well, in this case it's not just si. In this case, pardon me. So that's going to be S1, and then that's going to be S2, and then for each of the customers going down the columns, that's going to be demand 1, demand 2, demand 3, and all of them are also parameters because they're numbers that we know go with the problem, but in the more general sense, we don't know what they are yet. So we can kind of see that we basically the x1j, x2j, and then mj. That effectively what we are doing is that we are going down the demand column. So x11, x21, x12, x22, x13, x23. Now the other thing is that if you don't know how to read the notation, you notice that the for all j. So in essence, what this is also saying is that it's saying for all j, which in this case customers. For all customers, they have a demand constraint. And demand constraint is basically the amount of resources that's going to the total amount of resources that's going over to the customers, as said before, going down each of the columns. So that's what's happening there. So similarly, and sorry, one more thing. And so for all j is in this case, like say we have 3 customers, that means there's going to be 3 demand constraints. So in this case, j is going to be equal to 1, 2, and 3 because there are 3 customers in the little mock example I built up at the bottom, or in the previous, or in the example given in the previous video. So similarly, for supply, we have the similar scenario happening. So notice the indexes with I, so I1, I2, IN, and then SI for all I. So what's happening there is that if we are going by the different dimension now, and where I is equal to 1 and 2, because we've only got 2 supplies in the example, and then in this case we are going across the rows to effectively formulate our constraints from there. So like before, we've only got 2 suppliers, and as such we only need 2 constraints in total for the supply. So that gives us our resulting LP of a general form where we've covered our constraints here, and then that's our non-negativity. So what do we make of this objective function, which I should really clarify, that should be a big C there. So for this objective function, if you're not familiar with the sigma notation is kind of just a very easy way to say, okay, we're going to be adding up a bunch of these. So what's actually happening? What's happening here is that we've got the cost ij. So if you remember the table of distances or costs, so one way we could look at it is say, okay, we've got C11, C12, C13, C21, C22, C23. And that's kind of like what I tried to describe in the previous video, but effectively to get the total cost, we just need to add them all up together. And so effectively what this first sigma is this big sign there, if you couldn't follow me. So what's I'm not sure what just happened there. There we go. So what's happening is that we are summing up over the i's, which in this case is the factories, and then we're summing up over j, which is the customers. And then this is the cost, and then so in this case this is the cost, and this is the decision variable that basically we will determine how much of whatever product it is that we're going to transport from one supplier to one customer. So that's kind of the more general form of the transportation problems in general. Notice that even though I say balanced in the title, technically the formulation that's given is reasonably flexible. Just be warned that in some sources, or at least most sources I've seen, transportation, the balanced transportation problem is when these are equality constraints, because they want to distinguish between balanced transportation problems and unbalanced transportation problems. So, and the unbalanced transportation problems is that assumes that if that the total supply is equal to the total demand, which for the most part means that you need to adjust the transportation problem formulation. However, with this particular formulation as given here in this video, we won't really need to worry so much about that. So after that we'll look at some ways of solving. We'll look at the simplex method, which is a more automated process of solving these larger kinds of linear programming problems, which we cannot necessarily solve with the graphical method. So until then.